talks about Newton's three laws. And Newton's three laws are very basic ones. We're going to actually, today, for the rest of the class, I will talk only theoretically about the three laws. And starting on Thursday, we're going to start solving problem on chapter 5. Chapter 5 says that Newton said that any object will stay at rest. It will never move unless something from outside acts on it. You can go back. This is Newton's first law. Everything tends to stay at rest or to move in a constant speed unless there's something else acts on it. Look at this. No. My mobile. I'm going to risk that. Okay. If I move that, my mobile will move with it. Slowly, my mobile will move with it because there's friction between the mobile and the paper. But if I move it really fast to overcome the friction, now my mobile will tend to stay at rest. It will not move with me. Okay? So friction made it move a little bit. But if I do it a little more faster, it stayed at its own place. It did not move. And this is Newton's first law. Everything tends to stay at rest unless something act on it. And that's Newton's first law. Not only stay at rest or move with the constant velocity. If you have an object that moves with the constant velocity, it will not change that velocity unless you act on it by something else. That's Newton's first law. Newton's second law stated that if you have someone pushing or pulling you, that means that you're going to move with an acceleration. Your velocity is going to change. So if I push Nagy or I pull him, then Nagy will move with an acceleration. His velocity is going to change. That means that he's going to move with an acceleration. And that's Newton's second law. Newton went a little bit further than that, and he said actually if you have more than one force acting on an object, some of those forces will equal to the mass of the object times the acceleration, times its acceleration. So Newton's second law, which is very important, said or stated that sum of the forces will equal to mass times acceleration. If you have more than one force acts on an object, all those forces, if you add them together as vectors, because force is a vector, that will equal to the mass of the vector times its acceleration. Now we come to multiplication of a scalar by a vector. Mass is a scalar quantity. Do you remember that? Acceleration is a vector quantity. If you multiply a scalar quantity by a vector quantity, you get a vector. Okay? So that means that the acceleration and the force, total force, will be along the same direction. They will have the same direction. Yes? Sum of forces will equal to mass times acceleration.
So you just call it as F?
Yeah, same thing. That's Newton's second law. So, what's your name? Ahmed. Nagy. Stand up. Ahmed. Okay, so actually, Ahmed is going to pull Nagy in his direction. And I'm going to, wait. And I'm going to pull Nagy in my direction. He's going to pull Nagy with the force along that direction. And I'm going to pull Nagy with the force and along that direction. And one of us will put more force than the other one, and accordingly, Nagy will move in the direction of that force. Okay. So what happens now, if you have force along that direction from Ahmed on Nagy, that's F1, and force from me on Nagy, guys, thank you, along that direction, those two forces, if we add them together, we get, as like what Sharif said a minute ago, a net force in the direction of the stronger one. And the object will move with an acceleration along that direction of the net force. But sometimes, actually, Ahmed, what's your name? Mustafa? Okay. Guys, we're going to push Nagy with his chair, and you're going to push him in that direction, and you're going to push him in that direction, and I'm going to push him in that direction. Okay? So you're going to push him into that corner, you're going to push him into that corner, and I'm going to push him in that direction. Okay? Let's do it. Can we move in here? Can we move in here? Can you move the chair in here? Okay. And we need to find the net force. Okay, guys, do you know your role? You're going to push him into that direction. Into that direction, I'm going to push him here. Okay. Push. So what happened? Actually, Mustafa pushed Nagy into that direction, which means that if we analyze that into two, you can go back so you can see me actually. You're not here only to push you around, you know. So Mustafa pushed Nagy along that direction, which means that he put forces on Nagy into two directions, X and Y. To resolve that force into two components, a component along the X and a component along Y. And Ahmed pushed Nagy along that direction. That means that he put also two components, one along the negative X and one along Y. And I tried to push him along the negative Y. The two components of Ahmed and Mustafa were much stronger than my Y component. So they overcome me, and their 2X component canceled out. That's why Nagy moved into that direction at the end. What I did now, I just added vectors. And those vectors happen to be forces. So now, this is Newton's second law. Sum of the forces equal mass times the acceleration. Now I'm going to push Nagy one more time. Okay? Nagy. And he's not moving. What does that mean? Oh, okay. We need to listen to each other. I'll start with Minna.
The force, the friction,
Mhm.
the Nagy mixed with the floor is greater than your force.
Okay. This is a good statement. Minna is saying that actually your force, the force that I'm exerting on Nagy, is not high enough, not big enough to overcome the friction between the chair and the floor. Okay? If there is no friction, in what direction will Nagy move? So this is the direction of the force. And can you guys guess the direction of the friction force? So it's always opposite to what? Opposite to what? Friction force opposite to what? No. Direction of motion. If there is a motion, if Nagy is to move, in what direction will he move? That direction. That means that the friction force is opposing that motion. It has to be along that direction. The friction force is always in the opposite direction to the motion.
But isn't the force, if you're exerting a certain force on something, isn't it moving in the same direction as the force?
Yeah.
Okay, so you can say direction of the force, right? Or the direction of the
friction.
Not always, because you'll find cases that's not really true. Now, look at this little demonstration again. I'm going to tell that why that object is not moving down along that plane. But there is a gravitational force now that should move him down, move that object down, right, that way. Because there is a friction in that way. Yeah, because of the friction force, and the friction force direction is always against the direction of the motion. If this is to move, it's going to move along that direction. If it's to move, it's going to move along that direction, which means that the friction force is preventing it from moving. That means that the friction force is along that direction. But in this lecture, in the remaining 15 minutes in the lecture, and the next class, I will ignore the friction force for now. So I'm going to assume that everything we do is a frictionless surface. We don't have friction for now, for like a class or two. Then we're going to include the friction later on. So now what I did is I introduced to you two laws of Newton's. First law and the second law. First law that said that everything would love to stay at rest or move, or it should move with a constant speed unless you act on it by an external force. You act on it by an external force. That's Newton's first law. Newton's second law says that sum of all the forces will make the object move with an acceleration equal to A, and the sum of all forces will equal to mass times acceleration. Newton's third law, it says that we're not angels. This is what Newton's third law says. If you hit someone, he will hit you back. That's Newton's third law. For each action, there is a reaction, equal in magnitude and opposite in direction. And do you skate? Guys, do you skate? Did anyone try to skate?
Yeah, try.
Try, yeah, good. If you go skating and you stand in front of your colleague and you push him in that direction, what's going to happen to you? You're going to move in the opposite direction. I'm talking about skating because when you skate, we minimize the friction. So you can observe that phenomena of Newton's third law.
Oh, ice skating?
Ice skating, yes.
Yeah.
Or roller skating. Oh, no. I said it's valid for everything. But I said you can observe it only when you minimize the friction. You can see it by your eye when you minimize the friction. So if you go skating and you push your colleague, he doesn't push you at all. If you just push him in that direction, he's going to move in that direction, and they're going to move in the opposite direction with the same exact forces. So if you push a big guy and you're just a small guy, what's going to happen? He's going to move a small distance. He's going to have a small motion, small acceleration, and you're going to have larger one. That's Newton's second law. He will move with an acceleration equal to his mass. He will move with a force equal to his mass times his acceleration, but because he has a big mass, his acceleration is going to be small. And you're going to move in the opposite direction with the same force. But because you have a smaller mass, you're going to move with a higher acceleration. Okay, one more thing.
Push the walls.
Yeah?
Something happens.
Yeah. Not only that, something that will it might amaze you. Do we have a force from Earth on that object? What kind of force do we have? Gravitational force. And that gravitational force will attract that object to the Earth. So how come that object does not attract the Earth to it? It's the difference in the mass. It does attract it. There is a gravitational force between that object and Earth that attracts the Earth to that object, same as the force that attracts that object to the Earth. That's Newton's third law. But because this has a smaller mass, it moves with a high acceleration, and Earth has a big mass, it moves with a very, very small acceleration, that's almost zero.
But not zero.
Yes, not zero. If you're talking about 0.000000001 is not zero, then it's not zero. Yes, Farida.
Is gravity electromagnetic?
No. No. We'll get into that. And when we go into Physics 112 next semester, you're gonna, if you take Physics 112 in the next semester, what you're gonna do is you'll find that there is a similarity between electrostatic forces and gravitational forces. Okay, now guys, this was just an introduction to chapter 5. This is Sir Newton, Isaac Newton, and there is a little bit of a history about Newton. He was born in 1643, and he's a brilliant guy. He published his famous book Principia Mathematica, but he died in 1727. And he gave us the 3 Newton's laws that we should still apply them till now. And those are the 3 laws that we talked about them. And we said, when we talk about Newton's third law, the force, I forgot your name. Vanessa. That third law says that the force F from object A on object B equal to the force F from object B on object A, but in the opposite direction. That's why we have that negative sign. Okay. So we talked about Newton's first law. Before we go on, Newton's first law is valid only if you're talking about objects that that's at rest or moves with a constant speed in IRF, in inertial reference frame, the IRF. And if you remember, we have defined last time what is IRF, inertial reference frame. That's a frame that does not move, or it moves with a constant velocity. Does that mean, when I did my little experiment in here now, does Earth is a good inertial reference frame? Can we consider Earth, though it rotates, as an inertial reference frame? Focus. Let's find out. We know that Earth rotates, and actually it spins around itself one time. Earth rotates around its center one time every 24 hours. So it goes a distance equal to 2 by r. 2 by times its radius, rotates around its center. It goes that distance in 1 day. So 1 day, that's equal to 8.6 times 8.64 times 10 to the power 4 seconds. This is 1 day in seconds. And the radius of the Earth is 6.4 times 10 to the power 6 meters. That's 6 million meters. Now let's calculate the acceleration that the Earth moves with when it rotates. Centripetal acceleration. That's v squared over r. Or in other words, that's omega squared r. Omega squared means that the Earth is rotating one complete cycle, which is 2 pi. It rotates 2 pi in 1 day. That's omega. 2 pi over t, that's omega. It moves an angle of 2 pi in t equal to 1 day. So if you divide 2 pi by that number, this is omega. So omega squared r, this should give us the angular acceleration of Earth. And if we do that calculation, you'll find that the angular acceleration of Earth is 0.034 meter per second square. And that's almost 1 over 300 of g, acceleration due to gravity. The acceleration the Earth moves with is almost 1 over 300 of the acceleration due to gravity. That we can consider that to be 0. that means that we can consider Earth to be a good inertial reference frame. Sharif.
But isn't it also because we are all, like every object has the same, like this acceleration acts on every object. Like we are accelerating at this rate as well. So it could be a good frame of reference if we're on Earth, but if we're outside Earth,
No. But if you are in a reference that moves with an acceleration, you cannot consider that reference to be an inertial reference frame. By definition, an inertial reference frame is a frame that does not move at all or moves with a constant speed. But if it has an acceleration number that's significant than that, then we can consider Earth to be as an inertial reference frame. Okay, I just proved to you.
I understand that.
Okay.
I mean, for a person in space,
Mhm.
this angular acceleration would be apparent if he's really not moving compared to Earth.
For a person
Like
in the space.
Outside,
Mhm.
if you're not on Earth,
Yeah, if you're flying on an airplane,
maybe, and you're totally not moving,
Mhm.
stationary,
chopper. Hmm.
yeah, the movement of the Earth would be apparent somehow.
Yes, it will. Very, very small. Okay, it's very, very small. That's Newton's second law. And the Newton's second law states that the sum of the forces equal mass times the acceleration. And Sharif, you mentioned the word net force, and here it is in the presentation. The sum of the forces, if you add them as vectors, then we sometimes call that the net force acting on the object. Equal mass times the acceleration. And if we talk about the units for the force equal mass times the acceleration. Mass has the units of kilograms. Acceleration has the units of meter per second square. Then the units for the force, that's kilogram meter per second square, and we are going to call kilogram meter per second square, we're going to call it Newton. 1 kilogram meter per second square, we will call that Newton. Now look at that object. You have an object F1, object that has a mass m, and there is two forces act on them, on that object, F1 and F2, and along those directions that you see. What is the acceleration of that object? So what to do? We add those two vectors as vectors. So those two forces as vectors. And do you remember how did we add vectors graphically? We draw the first vector, that's F2, and from the tip of F2 we draw F1, and that line is going to represent to us the sum of F1 and F2, and this is going to be mass times acceleration. This is going to be the net force, and if we know that what is the net force, then we can simply find the acceleration. Acceleration will equal to the net force divided by the mass of the object. This is graphically. Mathematically, we should resolve those two forces. No. Mathematically, we should first draw our coordinate system. Find out what is our x coordinate and what is our y coordinate, then resolve those two forces on the x and the y axis and add them as an ij component. Okay guys, so first we have to find F1, the x component of F1 and the y component of F1, then find the x component and the y component of F2 and add them. And if you do that, you get the resultant of F1 and F2, or the net force. Newton's second law can describe a motion in 3 dimensions. If I put a force at F, this is X, this is Y, and that's Z. If I put a force F on that, I'm going to push it along the X-axis. So the force is along only X-axis. And if we apply Newton's law on that, to describe that, we'll say that sum of the forces equal to mass times acceleration. The only force here is along the x-axis. But if I push it along that direction, then we have a component that moves the object along the x-axis and a component that moves it along the y-axis. Then we have two for the Newton's second law. The first component will say that the force along the x-axis equal mass times the acceleration along the x-axis. The second component will say that the force along the y-axis will equal to the mass times the acceleration along the y-axis. No. Which one is the same?
The x direction, the y direction.
No. If you move with the 45 degrees, then it's going to be the same. But if you move with the 60 degree, then the x component is going to be f cosine theta, and the y 60, and the y component is going to be f sine 60.
But the mass of the acceleration will not change.
No, the x acceleration and the y acceleration is going to be different. They will be different. They will be equal only if you move with a 45 degrees. Other than they will be different. But if I do this, now we have force along the x-axis, y-axis, and the z-axis. Then we should actually get components for Newton's second law, one along the x-axis, and one along the y-axis, and one along the z-axis. Then apply them. Okay guys, so I'm going to stop here. I'll see you.